In this video, I'll describe a method used to solve ordinary differential equations. This is a better approximation than the Euler method, which is described in another of our videos. The Runge-Kutta method is a fourth order approximation. The idea is we have initial conditions, namely a certain location, a certain value of x, we know the value of y, and then we have an ordinary differential equation that relates how y changes as we change x, and that's a function of x and y. What we're going to do in the Runge-Kutta method is use a recurrence formula. Say if I know a value of y, then I can make a small step, and the step is to say x n plus 1 is equal to x n plus h. So we'll make a small step in h, calculate the new value of y that corresponds to the x n plus 1. And we have this term here that's a function of x n and y n and the size of the step. Smaller steps will give us more accurate calculations. Of course, this is something that in a computer program can very easily be done to step through. Programs can be more sophisticated than this, but this gives you a good idea of how these programs work. So what I'm going to do is write down the formula for T4 and then discuss what the terms are in it. The T4 is 1/6 times the summation of the 6 terms essentially. K1 is just a function evaluated at x and y, so at x and y n for our given condition. K2 is a function evaluated, but now x plus half the step size, and y plus half the step size multiplied by the function, K1. K3 is very similar, except it's K2 here, and then K4 is evaluated at the full step size, and K3 is here. And so this gives us a better approximation than, say, the Euler method, which just we used a function at the previous point. And the fourth order approximation means if we were to decrease the step size, so instead of h, if we used h over 2 as our step size, then we reduce the error by a factor of 2 to the 5th. We can get fairly accurate measurements using this Runge-Kutta. So what I want to do next is apply this formula to a simple differential equation, look at the first few steps to make it clear how we're doing these calculations on the computer. So let's look at this example. I've written a simple differential equation. We could certainly solve this analytically, but what we're interested in is the technique. And we're going to assume that at x 0 equals 1, y 0 equals 2. So this is our initial condition. And then we use the step size to calculate y at a larger value of x. So I've written down the recurrence formula, and then I've substituted in the numbers. So y0 is 2. The step size here is 0.1, and then k1 plus 2k2 plus 2k3 plus k4. And so we need to calculate the values. K1 is just a function evaluated at x0 and y0, which is then 3x0 squared times y0. So that's K1, and similarly we calculate the other values, K2, 3, and 4. So I've written the recurrence formula term now for K2. It's evaluate x0, which is 1, plus the step size 0.1 divided by 2, and then again step size over here 0.1, and then now the value of K1 that we just calculated. So we have the value for K2, and we do the similar things to calculate K3 and K4. So here's the values calculated for K3, where we're using now K2 that we calculated in the previous step. We get the value of K3, and to calculate K4, now we use step size h, so this is 1.10, and we're using K3 in this calculation. Once we have these 4 values, we can calculate y1. So y1 is y0 plus the step size, h over 6, k1 plus 2k2 plus 2k3 plus k4. So I'll substitute these values in. And so substituting the values we calculated for k1, k2, k3, and k4, we get y1 that corresponds to the next one value of 1.10. Well, this is much more accurate than the Euler method calculation. And then we continue to step through. We can get y2 as y1 plus ht4 evaluated at x1 and y1. And the same idea, we can calculate the function as we move through, where k1 in this calculation is a function now of x1 and y1, the values we just calculated. This is then the technique that's used in numerical programs like polymath to solve ordinary differential equations. And we can certainly solve simultaneously a number of ordinary differential equations with this technique.